These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. Well, to start with, why don't you remind me, what is the symbol for electric charge?
Q.
And what's the unit for charge?
Coulombs.
And is that a vector or a scalar?
It's a scalar.
So is that the kind of thing we would have to break into components? No. Good. All right, what's the symbol for electric force? How about, what's the symbol for electric field?
E.
Good. Now, what's the unit for electric field?
It's joules. No. I'm totally blanking. It's I don't remember.
Looks like that would be a good thing for us to
Yeah.
review. Now, this is one of the most important units to commit to memory, so we want to just keep reviewing this over and over because, unfortunately, most students never really get any intuition for what electric field means. All they're doing is plugging into formulas, and one reason for that is they don't remember what the units are. Well, the unit for electric field is newtons per coulomb, and that really should give us much more intuition for what the electric field means.
Yeah.
For example, suppose that the electric field at a point in space is 8 newtons per coulomb. Well, do you remember what was our interpretation for that? Remember we said that we could put the number 1 down here on the bottom, and then we would say, well, this tells us that if we put a 1 coulomb test charge here, it will feel 8 newtons of force. So the electric field tells you what the force would be on a 1 coulomb charge, and it's a lot easier to remember that if we remember what the units are. So we want to just keep reviewing that. Of course, if there was a 2 coulomb charge here, it would feel twice as much force, or 16. The electric field would still be 8 newtons per coulomb, but the force would be 16 units if this was a 2 coulomb charge. Is the electric field a vector or a scalar?
It's a vector.
So do we have to break that into components? Yeah. Okay, and what's the unit for electric force?
Newtons.
And is that a vector or a scalar?
That's also a vector.
So that is the kind of thing we'd have to break into components as well. Well, that's just a review of some of the stuff we've gone over in previous sessions. And I think, so this kind of flow chart shows us how the source charge creates an electric field, and then the electric field exerts a force on the test charge. And then there's 2 different arrows here, which means that there's 2 different tasks you might have. You might have to go from the source charge to the electric field, or you might have to go from the electric field to the force. And over both of these arrows, we have to write how to figure out the directions. What's the relationship between the source charge and the direction of the electric field? And over here, what's the relationship between the direction of the electric field and the direction of the electric force? And we also talked about how to find the magnitude of the electric field from the source charge. You could put that formula here, or the magnitude of the electric force from the magnitude of the electric field. We could put that there. Do you have that handout with you?
Yes.
I just asked because you should find that and throw it out, because I have a new improved
really?
version of that. Yeah. So when you find that, you can just throw that out. Here's the new and improved version.
Okay, thank you.
All right, so here we are. This has 2 sides now, but the side we went over last time was the side on electric field and electric force, and that shows our flow chart here. One improvement I made here is I actually added the units for each concept because that's so important. So we need to know, say, the units for electric field are newtons per coulomb, or the units for charge are coulombs. And above the arrows, reviews again how to figure out the directions, and below the arrows how to figure out the magnitudes. One of the main things you did in your last homework was figuring out the magnitudes for this left-hand arrow, how to go from the source charge to the electric field using Gauss's law. Now what we're going to do today is we're going to do a similar flow chart. Because source charges, besides creating an electric field at a point in space, can also create an electric potential at a point in space. The symbol for that is V. Just like the electric field is a property of space, the electric potential is also a property of space. It's not a property of an object, but of the space. And then you can use the potential to figure out what the electrical energy, the electric potential energy would be. For a certain point in space, we use the symbol capital U for that. I'm sorry, what the electric potential energy would be for a collection of objects, U. So this is going to be a very similar flow chart. Hopefully having two similar flow charts will make it easier to remember the relation between all these different concepts. So source charges are sources of electric fields and electric potentials at points in space. The field exerts a force on charges that you put at that point in space, and the potential at the point in space lets you figure out what the energy of an object would be if you put it at that point in space. And now again, we're going to have to figure out what the formulas are that go around these arrows. And also, we're going to have to try to get some intuitive understanding for these concepts. So remember, we just reviewed the intuitive understanding of the electric field. What's our intuitive understanding of the electric field? The electric field tells us what the force would be on a 1 Coulomb charge. Okay. By the way, just to review, what are the units for the electric field?
They are newtons per coulomb.
That's right. Okay, so we want to just keep reviewing that until that comes to us quickly. That explains why the electric field tells us how many newtons of force would be experienced by a 1 Coulomb charge at a point in space. All right, and now we're going to try to get a similar flow chart that relates source charges, electric potential, and the energy of test charges. Well, let's start with first of all, we have to review the concept of electrical potential energy. Well, let's review what we know about gravitational energy. So what do we usually say is the gravitational energy of an object that's on the ground?
0.
Yeah. Remember from last term, we usually said that when you're in the ground, your energy is 0. Remember the formula for gravitational potential energy is mgh. Well, if your height is 0, that would give us an energy of 0. Then the further you are from the ground, the higher your energy is. All right, what are the things that we need to know about this? Well, first of all, if an object is free to move, is it going to tend to move to increase or decrease its gravitational potential energy? Do objects want high or low potential energies?
Low.
Yeah, everything wants to lower its potential energy. For example, if I release this ball over here, it's not going to move up to higher potential energies, it's going to move down to lower potential energies. So when are things happy? When they're at high energy or low energy?
Low energy.
Yeah, everything wants to lower its energy. That might seem counterintuitive because people are happy when they're peppy and full of high energy. But in science, low energy is good. Everything wants to lower its potential energy. That's going to turn out to be very important. Everything wants to lower its potential energy. Now suppose I told you that the energy of this object, well, do you remember what the units are for energy?
Yeah, joules.
Good. So let's say I told you that this object has 6 joules of energy. What does that really mean? Well, what that means is it would take 6 joules of work to move it from the ground to here. Your energy tells you how much work it takes to go from 0 energy to where you are right now. So it would take 6 joules of work to move from here to here. By the way, remember that work is force times distance, so joules must be Newton meters. So we could also call this 6 Newton meters.